السلام عليكم ورحمة الله وبركاته. الحمد لله والصلاة والسلام على رسول الله صلى الله عليه وسلم. Inshallah, today we are going to give a revision before the final exam. First of all, I want to tell that today's revision is not designed to display the similar questions to that you will see in the final exam. We want from this revision to teach you how to think in solving the problems in the exam. Also, we are not going to cover the whole syllabus in this revision, so just we want to show you the way you need to think to solve the final exam. As I said, you may see some questions in this revision, but you may miss this type of question in the final exam, and also you may see some questions and you may find similar questions in the final exam to these questions. By the way, the final exam will be multiple choice, 40 questions that will deserve 60 marks. Every single question will deserve 1.5 mark. So first of all, you need to split the whole time of the exam, which is 2 hours for the 40 questions. You should not spend too much time in a single question, because that will lead to missing other questions. By the way, you will answer the exam in the bubble sheet that you have seen in the midterm. So all the questions will be answered in this part, the part that is dedicated for the multiple choice questions, this part. So you will have 40 questions, so you will answer in the first column, second column, third column, and the fourth column. Make sure to highlight only a single choice, like A or B or C. As you know, choosing more than one answer will cancel the question. I want to also to emphasize that you need to write your ID properly here in this part. Make sure to highlight a single cell in a single column. I wish you spend some time to revise your ID in the exam, because that may make troubles in the correction sections. Let me now show you some of the questions that will be similar to the questions you will see in the final exam. The questions actually are classified to 2 types. The first one is the conceptual. So we may ask about certain laws, certain phenomena, certain behaviors, and the other type is solving problems. So you will need to use your calculator to implement the facts and the laws that you have studied during the semester. So the first question is saying, if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. This is a statement of what? Of what? The first choice is His law. The second choice is Raoult's law. The third is Dalton's law. and the fourth is Le Chatelet principle. So the answer will be, of course, Le Chatelet principle. So this is one of the questions that is asking about the statements that you have taken in that course. This is, of course, the Chatelet principle that we studied in the chapter of equilibrium. The other question, the following factor or factors, as you can see here, because you may observe that several answers in the choices may fit in the gap here. So we are sometimes in the question you can see that we put S between brackets here to open the opportunity for choosing more than choices. So the following factor can certainly affect the solubility of a given solid in a certain solvent. Number one, the temperature. Number two, the pressure. Number three, the nature of the solid and solvent. Number D is all of them. Of course, the answer would be all of them. All of them will affect the solubility, and we studied every single one alone, the effect of every single one alone in the chapter of the solution. So the answer will be all of them. Of course, these types of questions may not consume more than a few seconds. So you do not need to spend too long time, as I said before, because other questions may consume longer time. Another question, a solution containing more solids than the equilibrium amount that tends to move to saturation under proper condition is called the dot solution. Which one? Is the saturated solution, the unsaturated, the supersaturated? Missing information. So which one we will select for this? Actually, for saturated solution, this is the solution containing exactly the amount required, the amount of solids required to form the saturated solution, but more than this amount is given for the supersaturated solution. So the answer will be supersaturated solution. Which of the following except dipole-dipole attraction between molecules? This is very important actually. The molecules that will exhibit dipole-dipole attractions should have a difference in the electronegativity of the forming atoms. So the first one is HF, the second one is oxygen molecule OO, the third one is chlorine molecule ClCl, the third one is hydrogen molecule HH. Of course, as you can see here, for the oxygen and chlorine and hydrogen, these are the atomic molecules or homonuclear molecules. They do not have any difference in the electronegativity of the composing atoms. The only one that has a difference in the electronegativity of the constituting atoms is HF, and therefore this is the only one that will have the dipole-dipole attraction in that molecule. So the answer is hydrogen fluoride. Which of the following except only London dispersion forces? As we mentioned in the course, some molecules may have several types of forces inside. They may have hydrogen bonding, they may have dipole-dipole attractions, they may have as well London dispersion forces, but certain molecules which are non-polar only have the London dispersion forces. So if we are asked to select between water, methanol and hydrogen fluoride and chlorine, so the answer will definitely be chlorine, because chlorine is the only molecule that have no dipole moment. no dipole moment. So this is the only type of force existing in chlorine is the London dispersion force. The rate of vaporization of a liquid increases when the temperature increases, when the surface area of the liquid increases, when the intermolecular force between liquid molecules are weakened. Of course, all of them fit in the answer here. So the last one is all of the above. So the answer will definitely be all of the above. The number of atoms per unit cell in a certain metal in the body-centered cubic lattice is how many atoms in the body-centered cubic lattice, BCC lattice? How many atoms here are they? One single atom, two atoms, three atoms, four atoms? So if you look to the crystal lattice of the BCC as we described in the lecture, we will have 8 atoms in the corners of the cube. Here every one participates by 1/8 to that unit cell. So overall the atoms in the corner contribute by a single atom, and we also have another atom in the middle of the box here. So overall we will have 2 atoms. So the answer will be two atoms. The general equation for non-ideal gas is represented mathematically by which one we have taken for the non-ideal or the real gas? This one actually, you remember, this is the general gas law, which is describing the behavior of ideal gas, not the non-ideal. Okay, so this answer is wrong. The other one describes the partial pressure of a single gas in a mixture of gas. This is a description for Dalton's law, and the Dalton's law is actually describing the behavior of ideal gases as well. So the third one here is that equation, but I want you to focus and to pay attention to the signs here in that equation. If you look, when we describe the van der Waals equation that describes the behavior of real gases or non-ideal gases, we did 2 corrections for the ideal behavior. The first one is to subtract the volume of the gas molecules from the volume of the container. And as I mentioned, that this correction will increase the observed pressure. As I said, as you can see here, this is a minus sign, so the denominator here will be lower, which means that the observed pressure will be increased. The other correction here is given for the pressure, which is resulted from the attractions between the gas particles. So we will consider the attractions between the gas particles effective here for the real gases. But if you remember, we stated that this correction will decrease the observed pressure, not increase. As you can see, this sign in the van der Waals equation is minus, not plus. So if I gave you the equation and I put here plus, this indicates that this answer is not correct, is wrong. So replacing the minus with a positive sign here indicate that this answer is wrong. So I want you not to get confused here, and to see the equation without any precise inspection for the signs, for the properties and the condition of the equation itself. So of course this answer is wrong for this question. So number D, none of these. Of course, you should select none of this. And this is actually one of the tricky questions that you may directly say this is van der Waals. Okay, number C is correct, and number C is actually wrong because of the sign here. The vaporization of water at room temperature is process with A dots delta H. The question is endothermic and the negative. Of course, we are selecting the first choice here for the first place here is the question, and the second one for the second place here. So the vaporization of water at room temperature is an endothermic with a negative delta H, endothermic with a positive, and exothermic with a negative delta H, exothermic with a positive delta H. Actually, the vaporization process, which is the conversion from the liquid to the vapor, this is endothermic process. Endothermic process. So you need to provide heat to vaporize liquid water, even at room temperature. And we discussed in the class that at room temperature the vaporization is feasible. If you left a cup of water for 2 days, definitely you will find that the level of water is getting smaller and smaller. So what happened actually is was the vaporization of liquid water. Can this vaporization occur at room temperature? Yes, it can. So what did it take the energy? It takes the energy from the atmosphere, to overcome the intermolecular forces between the water molecules to convert water from the liquid state to the gaseous state. So it is an endothermic process, and for every endothermic process, delta H should be positive. Should be positive because you are adding heat. You are adding heat to the system, so that the heat content will be increased. So the answer should definitely be endothermic and positive. So number B is correct answer. Real gas behavior is most likely sustained at which one? High temperature, low pressure, and low number of moles. Low temperature, high pressure, and low number of moles. Low temperature, high pressure, and high number of moles. High temperature, low pressure, and high number of moles, high N. Okay, so as you remember, we stated in the chapter of gases that the ideal behavior is sustained. The ideal behavior is sustained at low pressure, and high temperature. This is the ideal behavior, but and also it is sustained at low number of moles, because as the concentration increase, the deviation from the ideal behavior increase as well. So for the real gases, which one will be suitable for our answer now? Real gas should be sustained at low temperature, high pressure, and high N, and high low temperature, high pressure, and high N. So the proper answer will be numbers. Similar question. Boyle's law is valid at. Actually, Boyle's law is describing the ideal behavior. So this is the same question as if I asked you the ideal behavior is valid at. So most of the questions, most of the laws that we studied in the gas chapter are describing the ideal behavior, like the Dalton's law, the general gas law, the Boyle's law, Charles' law, Avogadro's law, the diffusion law, Graham's law. All these laws are describing the ideal behavior. So if I just asked you like this question, Boyle's law is valid at, so we will select the same conditions applied for ideal gas. So which one? As I said in the last question, the ideal behavior is sustained at high temperature, low pressure, and low number of moles. So the proper or the correct answer will be A. Which one of the following solution inspired the smallest depression in the freezing point? We have studied this type of questions in the colligative properties of solutions. So the selections now is 1 molar glucose, 1 molar sodium chloride, 1 molar iron sulfate, 1 molar potassium nitrate. As you can see here, all of them, they have the same concentration. And you remember from the colligative properties that these are the properties that depend on the concentration, not depending on the identity of the salt. So it doesn't matter this is sodium chloride or iron sulfate or potassium nitrate, as long as they have the same concentration, and also as long as they have the same Van 't Hoff factor or the ionization factor, they will display the same effect for the freezing point and for the boiling point. Okay, so now if you look to all the salts here, the sodium chloride, the iron sulfate, the potassium nitrate, all of them, they theoretically have a Van 't Hoff factor of 2. Only glucose will have the Van 't Hoff factor of 1 because it will not dissociate during solvation. It will not dissociate during dissolution in water. So only glucose will have the Van 't Hoff factor of 1. All of them will have 2. So we expect that 1 molar glucose will have the smallest depression of the freezing point. As you can see, colligative properties is independent of the type of the salt added but on its concentration. The one having the smallest Van 't Hoff factor will have the smallest delta TF. So the answer will be 1 molar glucose. The following figure depicts the BT plots for 3 materials. The first one is diethyl ether, ethanol, and water. This is a BT relationship, the vapor pressure and temperature relationship. And the question is, which one of them is more volatile at 20 degrees Celsius? Which one is more volatile? As you can see here, the more volatile one should have the highest vapor pressure. So basically, you can know that the diethyl ether is the correct answer here. So the answer would be diethyl ether. But also we can ask differently with this plot. You know, this is the 1 atmosphere, which is 760 torr, and the vapor pressure at 1 atmosphere here correspond as well to the boiling point of the different material. So if I asked you which one has the highest boiling point here, so water will be the highest boiling point. I may ask differently also to ask which one has the strongest intermolecular forces here. The strongest correspond to the highest boiling point as well. So water will have the highest intermolecular forces, or the strongest intermolecular forces among the whole materials. Ice floats on water at room temperature as a consequence of being ice has a lower vapor pressure than liquid water. Ice and liquid water have the same density. Ice is denser than liquid water. Ice is less dense than liquid water. Regarding the first choice here, ice has a lower vapor pressure than liquid. You remember in the chapter of liquids and solids, when we describe this figure, the relationship between vapor pressure and temperature, We refer that at temperatures higher than for water, of course, higher than 0 degrees Celsius, the vapor pressure of the solid will be higher than the vapor pressure of the liquid. So at room temperature, somewhere even after plus 5 years, we expect that the vapor pressure of the solid will be higher than the vapor pressure of the liquid, which is the opposite of the statement in number one here. So number A is wrong for this question. How about the density of ice and the density of water? Actually, the density of ice is less than the density of liquid water, and that's why ice floats on liquid water. So the proper answer will definitely be number D. So D is the correct answer. The average kinetic energy of oxygen molecules in a closed container increases with increasing the container's volume, container's temperature, container's pressure. Missing info. Actually, you remember from the KMT theory that the average kinetic energy of any gas depends only on the temperature. So the correct answer will be number B, temperature. Another question: which one of the following shifts the following equilibrium in the direction of the decomposition? This is an application for the Chatterley principle. This is calcium carbonate. It decomposes to calcium oxide and the carbon dioxide, and the reaction is endothermic because delta H is positive. How can we affect externally to this equilibrium to shift the equilibrium to right, to the decomposition of calcium carbonate? Is it by adding carbon dioxide? Actually, adding carbon dioxide will shift the equilibrium to left, not to right. By increasing temperature, if you increase the temperature, you shift the equilibrium to right. So this will probably be the correct answer, the only correct. Adding argon. Argon is an inert gas, and we remember from the Chatterley principle that adding an inert gas to the equilibrium of a given reaction will not affect the equilibrium position, will not shift the equilibrium in any direction. Decreasing the container's volume. How decreasing the container's volume will affect this equilibrium? If you decrease the container's volume, so you need to shift the equilibrium to the direction having the least number of gaseous molecules. So decreasing the container's volume will definitely shift the equilibrium to left, not to the right. So the only correct answer here is number B. Increasing the temperature will shift the equilibrium to the direction of the decomposition of calcium carbonate. The change in internal energy of a system is certainly positive when heat flow into the system and the work is done by the system respectively, or the surrounding and system and surrounding. Actually, you remember that the convention that we have taken in the thermochemistry chapter, that the Q will be positive when heat flows from the surrounding to the system, and also W will be positive if the surrounding exerted the work to the system. So the proper answer will be here is number D, is when heat flows into the system, which means that the surrounding will transfer the heat to the system, and also when work is done by the surrounding. This is the only case that ensures that the change in the internal energy will be positive, because I mentioned here certainly it should be positive. Actually, heat may flow into the system, and the work can be done by the surrounding, can be done by the system, and delta E still can still be positive depending on the amount of the heat flow and the work done. So, but it depends now on the value. So not in every case will be delta E will be positive. But I asked here is certainly it should be at all times should be positive. The only case here is to ensure that the heat flows into the system and the work is done by the surround. As I mentioned, some other cases like this one sometimes can be correct, and another one also can like number A here can be positive sometimes, but the only answer here that should be correct all the times is number D here, as flowing the heat into the system will make Q positive, and the exertion of work by the surrounding will make W positive. So overall, delta E should be positive all the times, regardless of the amount of heat supplied and regardless of the amount of work exerted. Delta E should definitely be positive for this choice. And actually, we select the most correct choice, So number D is the most correct choice. A device to measure the atmospheric pressure is called calorimeter or barometer or thermometer or viscometer. Which one? Actually, the pressure is measured by the barometer. So this is the correct answer. The SI dimension of pressure is Newton meter square, kilogram meter minus 1 second minus 2, kilogram meter second minus 2, kilogram meter squared second minus 2. This is an important part of chapter 1, the dimensions and the units of the different functions according to the SI system. You need to realize the difference of them. Actually, pressure equal to the force per unit area, and the force, the unit is Newton, and the area is meter square. So it's supposed to be Newton per meter square. Newton per meter square, not times meter square. So number one is wrong. But if you split the Newton here, the force here, to mass time acceleration, you will find that the proper unit of the pressure is number B, kilogram meter minus 1 second minus 2. You should be familiar with the units of the power, the unit of the energy, the unit of the force, the unit of the pressure. All these functions that you frequently deal with, you need to know the proper unit, and you should differentiate between the capital letters and the small letters, the small letters of the prefixes. You need to write the unit properly according to the system that we described in chapter 1. So the correct answer is number B. Gas A and the gas B are mixed together in a container at a certain temperature. The partial pressure of gas B will be this one. The partial pressure of B equal to XB times B total, or XB times the partial pressure of A, or this one NB over P total, or NB P total. Which one of this is the correct answer? Actually, number A is the correct answer. The partial pressure of a given gas in a mixture of gases depend on the mole fraction of that gas multiplied by the total pressure. So this is the statement or the mathematical expressions for Dalton's law. In the following phase diagram, the phase change from phase C. The phase C is supposed to be for the vapor phase or the gas phase. From phase C to phase A. Phase A is the solid state. So the conversion from the green part here to the blue part here. It is the conversion from the gas to the solid directly without passing by the liquid state. Is known as the deposition, is known as the sublimation, condensation, or liquefy. Actually, the correct answer is the deposition. And of course, the opposite of the deposition is the sublimation. So if I asked you the conversion from the solid state to the vapor state, the termination of this process or the abbreviation of this process is actually the sublimation. The correct number of significance figures, calculate this operation to the correct number of the significance figures. Is this the answer? Or this one? Or this one? Or this one? Which one is the correct answer? Actually, to make the calculations here, first of all, we need to run the process to the end before rounding off. So we add these two items together here, so the answer would be 1.820 times this number. So we will get the final answer here, which is 0.5967. Now we should look to the rules that we have taken for the operation of the addition here. Addition, we have a single decimal point here for this number, but here we have 3 decimal points. So the answer should contain only a single decimal point. So even if this is the answer that you have seen in the calculator, you should make a rounding off for this to 1.8. This number, we will multiply this number with this number. Now, this number has a 2 significance figure, and this one has 4 significance figures. So the rule for the multiplication, that the result should contain only 2 significance figures. So the answer will be 0.60. So the answer will definitely be number B here. So this is the correct answer. I'm sorry, here we missed to write the 0.6. We'll correct this in the PDF file, inshallah. Okay, another question. The number of capacitive zeros in 5800. How many capacitive zero here? Is this 0, 1, 2, missing info? Actually, what the definition of the capacitive zero is the zeros between non-zero digits. So, do we have zeros between non-zero digits here? No, we do not have. So the answer will be number A, which is 0 capacitive zeros. These zeros are called trailing zeros, and any zeros preceding the non-zero digit are called leading zeros. So we need to differentiate between the different zeros type. A sample of nitrogen gas, 2 millimole, if used through a pinhole in 5.5 seconds. It should take, how long it takes for the same amount, like 2 millimole also, but from the methane gas to fuse under the same condition. Is it, which one of these numbers is correct. So let us apply the formula that we have taken, that the rate diffusion of gas 1 over the rate of diffusion of gas 2 equal to the root mean square velocity of gas 1 over the root mean square velocity of gas 2. This is supposed to be equal to the square root of the molar mass of gas 2 over the molar of the square root of the molar gas of gas 1. So what you need to apply or you convert the velocity here, which is supposed to inversely proportional to the time taken. So URMS of gas 1 will be proportional, inversely proportional to T1, and URMS of gas 2 will be inversely proportional to T2. So you can substitute directly in this equation to calculate T2 for the methane gas, which is 4.16 seconds. So the answer will be number C, 4.16 seconds. At 25 degrees Celsius, a nitrogen gas pressure of 500 to 22 millimeter mercury, the solubility of the nitrogen gas is given by this number. This corresponds to a Henry's constant of I want to attract your attention to the units. Usually you should inspect the units. In the Henry's constant is asking you now to represent the Henry's constant in mole per liter at atmosphere. This is a sort of pressure, but in the question here is giving the pressure in millimeter mercury, so we want to convert this unit from torr or millimeter mercury to atmosphere to calculate the Henry's constant in this unit. So which one of these selections will be correct? So we will apply in the rule here the solubility of a gas is proportional to the pressure of the gas over that solution, and the constant is Henry's constant here. So we will substitute by this value. This is the solubility of the nitrogen gas, and this is the vapor pressure of or the partial or the pressure of the nitrogen gas over the solution. But it's giving here the pressure of the nitrogen gas in millimeter mercury, so we will convert this to atmosphere by dividing by 760 millimeter mercury. So now we can calculate K to be 6.8 times 10 to the power of -4, so the correct answer will be number C. As you can see, this question is a direct substitution in the law, but the trick here is the conversion between units. You should pay attention to every single detail in the question. And a question like this will not take more than a minute or 2 minutes in the exam. The average kinetic energy and density of carbon dioxide gas at 100 degrees Celsius and the 10 atmosphere are dots kg per mole and dots g per liter respectively. So we want to calculate the average kinetic energy and the density of the carbon dioxide, which are the laws that we will use here. The first one is the average kinetic energy, and you can remember from the Chem theory, the average kinetic energy equal to 3 over 2 RT, and the R here should be given by 8.314 joule per Kelvin per mole, and temperature should be given by Kelvin. So we'll calculate kinetic average kinetic energy to be 4.65 kg per mole. So this is the first item that the question asked about, the average kinetic energy. The second one is the density, and the density as you can see, equal to Pm over RT, where M is the molar mass of the gas. So we'll substitute directly here. As you can see, we used the value of the universal gas constant in the first part of the question as 8.314 joule per Kelvin mole, but in the second one we used 0.082 liter atmosphere per Kelvin mole. Actually, the selection of the R depends on the question, because here we have atmosphere, so we should use the R as well in this unit. But here is asking to deliver the value of the kinetic energy of the average energy in joule, so we should use the R value in joule as well. Okay, so you should. I will give you actually in the formula sheet in the exam the two values, but I will not tell you which one you should use in a given problem. You should select it properly depending on the request in the problem. Okay, so as you can see, this is the correct answers. So the correct answer will be number B. This is the correct choice, number P. The freezing point of a solution prepared by dissolving 10 gram of calcium nitrate, and this is the molar mass of calcium nitrate, and 100 gram of water is asking about the freezing point. The first of all, and is giving here the molar freezing point depression constant of water. So we need to, and these are the choices. So we need to apply in this question. The first of all, the first we need to calculate the molality of this solution. This is calcium nitrate, so we need to calculate the molality, and the formula here is used to calculate the molality. This is the number of moles per kg of solvent. Okay, so this is actually the mass of the solid, the molar mass of the solid. And this is the mass of the solvent in gram, and we bought here 1000 to convert from the gram to the kilogram. If you apply here with this information, so you calculate the molality to be 0.61 mole. After that, we calculate the depression, the freezing point depression here from the formula IKF times the molality. We calculate the molality, and the Kf is given here in that the question, and the I for calcium nitrate equal to 3, because the distillation of calcium nitrate will result in 1 mole of calcium ions and 2 moles of nitrate ions. So overall we will have 3 ions per 1 mole of calcium nitrate. So delta Tf will equal to 3.3. Is this the new freezing point? Because we will have 3.4 here. Is this the correct answer? No. This is the depression. How about the new freezing point? The new freezing point will equal to 0 minus 3.4, which is minus 3.4. So the correct answer will be P here. So you should differentiate between the depression and the freezing point of the solution. The heat of formation in kilocalorie of these compounds, mercury chloride, potassium hydroxide, potassium chloride, mercury oxide, water are given in the question, and is asking now to calculate delta H of this reaction. As I mentioned to you many times, you should first inspect the balancing of the equation. If you look to the balancing of the equation, is it balanced? Yes, it is balanced. So we will substitute next with these values. So delta H will equal to 2 times the heat of formation of potassium chloride plus 1 times the heat of formation of mercury oxide minus 1 times the heat of formation of mercury chloride minus 2 the heat of formation of potassium hydroxide. So overall the answer will be minus 0.005. Let me inspect again the values. This is for potassium chloride. Yes, correct. How about the mercurous oxide? This is plus. Yes, okay, correct. How about 68 point? This is for water. 68 for water. 0.4. So we need to actually water is not given here. We need the delta H formation of mercurous chloride. Mercurous chloride is 630.01 and the potassium hydroxide. So we need to revise this value. Okay. So this is the equation. Hg2Cl2 plus 2KOH will give 2KCl plus Hg2O plus H2O. So now is making putting the delta H formation for the products, and this is for water here, which is 68.4. And now starting to put the heat of formation for the reactants here. This is the 63. This is for mercurous chloride, and this is for potassium hydroxide here, and is multiplying here by 2 because the equation has a coefficient of 2 here. So overall the value will be minus 3.05 kilocalories. So the answer should be number B. So everything is correct, no problem. A sample of nitrogen gas has a volume of 1.75 liter at STB. STB, you know, STB for the gases here is 0 Celsius and the 1 atmosphere. How many molecules of nitrogen gas are present? How many molecules of nitrogen gas? So when the question is asking about number of molecules, you need to calculate first the number of moles, and you multiply the number of moles by Avogadro's number to calculate the number of molecules. So basically the process will start with the ideal gas law, BV equal to nRT. Which one we have here? We have the pressure, which is 1 atmosphere at STB. We have also the temperature, which is 0 Celsius or 273 Kelvin. We also have the volume here, which is 1.75, and you definitely you know the R constant, so you can calculate N. So N will equal to this value in the number of moles, and then you calculate the number of molecules by multiplying by Avogadro's number. So the number of molecules will be 4.7 times 10 to the power of 22. So that the answer is actually number D. Number D is the correct answer. Another question is the normal boiling point of liquid water, ammonia, is minus 33.4 degrees Celsius, and it has a heat of vaporization of 23.5 kg per mole. Its vapor pressure at minus 50 degrees Celsius should be dot torr. By the way, we are asking about the vapor pressure of ammonia, the same gas, but at lower temperatures. At lower temperature, definitely we expect the vapor pressure will be lower at lower temperature. Which one of this temperature will be valid? So we will use the Caliburn equation here, which gives the relationship between the vapor pressure of a gas and the temperature, which is a direct relationship. Or when we compare between the vapor pressure at two different temperatures, we use this formula. Make sure to write the formula correct, otherwise the values will be incorrect. So we'll substitute here, knowing that at minus 33.4, saying this is the normal boiling point. Normal boiling point means that that temperature is the boiling at 1 atmosphere. At 1 atmosphere, this is the meaning of the normal boiling point. And I'm not supposed to tell you in the exam that the normal boiling point is given at 1 atmosphere. So if I asked you for for water, for example, the normal boiling point for water, this is 100 degrees Celsius at 1 atmosphere. So to compare between two different temperatures, we know for water that it boils at 100 degrees Celsius and 1 atmosphere. So this information may not be provided in the exam. You should be familiar with this information, because I may ask you to calculate the vapor pressure at another temperature for water. So you need to recognize that water boils at 100 degrees Celsius and 1 atmosphere. The same is here for ammonia. Ammonia boiled at minus 33.4 degrees Celsius, and this is the normal boiling point, which means that this boiling point is at 1 atmosphere. So we will substitute here by 1 atmosphere or by 760 torr, okay, in that question, which is at the normal boiling point. And we want to calculate the vapor pressure at minus 50 degrees Celsius. So this is the B2. B2 is supposed to be by 316. 300. So the answer will be number C, 316. As you can see, this is the vapor. This is the vapor pressure of ammonia at minus 50, and this is definitely lower than 760. Is lower than, because the temperature decreased. So this is one of the elements that indicate that your answer is correct. The concentration of sodium hydroxide in a certain aqueous sample is 1 molar. How many milliliters of the sample contain 4 grams of sodium hydroxide? How many milliliters? So we want to calculate the volume of the sample containing 4 grams of sodium hydroxide. Is it 50, 70, 100, or 120? So we will apply here in the rule for the molarity. And is asking now about the volume, the V in milliliters. So this is the mass of the sample, which is 4 grams. This is the molarity, which is 1 molar. The molar mass can be calculated for sodium hydroxide, which is 40. So now the volume will be 100 milli. So the answer will be number C. Phosphoric acid can be prepared by reaction of sulfuric acid with phosphate rock. This is the structure of the phosphate. According to the equation, calcium phosphate plus sulfuric acid gives calcium sulfate plus phosphoric. How many oxygen atoms are there in 1.55 nanogram? So look at the fix here for the mass is nanogram, which is actually 10 to the power of minus 9. 1.55 nanogram of calcium phosphate. So we want to calculate how many oxygen atoms are there in 1.55 nanogram of calcium phosphate. This is the first part of the question. As I said, to calculate the number of oxygen atoms, you need to calculate the number of moles first of calcium phosphate. But at the beginning, let us check the balance of the equation. As I said, every single question, every equation you are given in the exam, you should inspect first the balancing of the equation. We have here 3 calcium atoms, but here we have only 1, so we'll put 3 here, which makes the sulfate 3 groups. So we'll add 3 here as well, and next we will put 2 in front of the phosphoric acid, because we have here 2 phosphate groups, so the balanced equation will look like this. Number 2, the phosphate rock, we want to calculate the molar mass of the phosphate rock, which is actually 310 gram per mole, and after that we will calculate the number of moles of calcium phosphate, which is basically the mass of the calcium phosphate, but we convert it from the nanogram to the gram, and then we divide it by the molar mass to calculate the number of moles. If you calculate the number of moles for every single mole of calcium phosphate, how many oxygen atoms we have? We have 2 times 4 oxygen atoms, so we have 8 mole of oxygen atoms. So for everything, how many moles here of calcium phosphate? We have 5 times 10 to the power of minus 12 mole. So we'll multiply this number by 8 to calculate the number of moles of oxygen atoms, and then we will multiply the number of moles of oxygen atoms by Avogadro's number to calculate the number of atoms, atoms of oxygen in the sample. So the answer will basically be number C, which is 2.49 times 10 raised to the power of 30. So the convergence from mole to molecules is important here in this question. A continuation for the same problem here, the same reaction for the phosphate rock with sulfuric acid, but the question is different here. Suppose the reaction is carried out starting with 103 gram of calcium phosphate and 75 gram of sulfuric, which is substance is the limiting reaction. This is now is asking about the limiting reaction. Again, we will check the balancing of the equation, which is very, very important here. The equation is not balanced, so we will balance it here as we balanced it in the last slide. And then we will check the number of moles provided here. So it's giving now is 103 gram of calcium. We will convert this to the moles, so it becomes 0.33. And for phosphoric acid as well, we will convert the mass to moles by dividing by the molar mass of sulfuric acid, which is 98. So we'll have here 0.33 mole of calcium phosphate, and we will have 0.77 moles of sulfuric acid. Look at the stoichiometry of the equation. For according to the stoichiometry, we need for every single 1 mole of calcium phosphate, we need 3 moles of phosphate. So for this number, we will need 0.99 of sulfuric acid. Do we have 0.99 of sulfuric acid? No, we do not. So sulfuric acid is deficient, so sulfuric acid is the limiting reactant. So sulfuric acid is the limiting reactant. Another question. For the reaction NaCl, this is the equilibrium between NaCl and NO plus Cl2, is giving the equilibrium constant, which is equal to 8 at a certain temperature, and is now asking to calculate the concentration of NaCl in mole per liter that must be put into empty 4-liter reaction vessel in order that the equilibrium concentration of NaCl to be 1 molar, and is giving these choices to select from. Actually, the question is very simple. You know, we apply the formula for the equilibrium constant at the beginning for this problem. The equilibrium constant is equal to the concentration of NO raised to the power of 2, because we have coefficient of 2 here, times the concentration in mole per liter, of course, of chlorine raised to the power 1, because the coefficient is 1, divided by the concentration of NaCl raised to the power of 2. This equal to 8.1. And these are the equilibrium concentrations. Now, we will see that we started only with NaCl at the beginning. So, at equilibrium, if NaCl is decreased by 2x, is decreased by 2x, NO will increase by 2x, and Cl2 will increase by x. Okay, so at equilibrium, we should have an equilibrium like this one. At equilibrium, 2x squared for NO, x for Cl2, and NaCl2 is supposed to be A minus 2x squared. A minus 2x squared. But he gave you the concentration of NaCl at equilibrium. At equilibrium, which is 1. Actually, 1 square equal to 1 as well. Okay, so the equation will be like this one: 8 equal to 2x squared times x over 1. So we will solve this equation to find the value of x. So x is supposed to be 1.26. This is the value of the x which display the concentration of Cl2, and if you multiply this with 2, that will give the concentration of NO. How about the initial concentration of A? As I said, the initial concentration of A is supposed to be A minus 2x. So we will have an equation A minus 2x equal to 1. A minus 2x equal to 1. A minus 2x equal to 1. So we'll solve this to find A, the value, the initial NaCl concentration, which equal to 1 plus 2x. And the x is calculated from here, so the initial concentration will be 3.52 mole per liter. So the correct answer will be number C. And coming to here, we ended up this presentation. Thank you for your attention, and I wish for you a successful exam, inshallah. See you in the exam, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.